So, but this question you should have an idea. So far, when we talk about dynamics, what I mean in general, as you see, is things evolving in time. That's what dynamics means. So dynamical systems means studying things that evolve in time. So for game theory and other things like that, we had, payoff functions, other things in physics like electromagnetic fields and things. These all have clear time evolutions. Right? Even in biology, you have populations that evolve in time. But in our universe, in cosmology, it's not so simple. And the reason is the following. So let me ask you, how many dimensions do we live in right now? Not string figures. In general, how many dimensions do we live in? 4. So what are those 4 dimensions?
3 space and 1 time.
Okay. So the claim is that we live in 4 dimensions, 3 space, 1. But we don't just live in space, and we don't just live in time. We live in space-time, so it's 4 dimensions. So it's not just space, it's actually called space-time. And this was actually not Einstein's original idea. It was actually due to, if you can believe it, Poincaré again. And related to Poincaré was, does anybody know? It was not a Greek though. It was Minkowski. And then Einstein. Yeah. And then Einstein kind of took the ideas and put it forward. But the idea is that you cannot separate space and time. They're one entity. So if you want to picture our universe as a 4-dimensional manifold, then any event in our universe is labeled by 4 coordinates. x1, x2, x3, and then a time coordinate. So it's space-time. The point is you cannot separate these two. They are on equal footing. That gives you a problem when you're trying to understand dynamics, because then what does it mean for something to evolve in time? You see the problem. So the way you do this, in our universe, we want to understand the dynamics of our entire universe, how it's evolving. It's a problem because it's space-time. So how do you talk about something evolving in time? Well, what you do is, and I'm skipping about 2 months of general relativity lectures here, but what you do is you take your 4-dimensional universe and you apply what is called a foliation. And what this foliation does is it takes 4 dimensions and splits it into 3 plus 1. And so 3 spatial coordinates and 1 time. So in other words, you take your 4-dimensional structure and you break it up with the preferred time-like structure. I won't look at it. And you have a bunch of 3-dimensional slices that you are evolving in time. So this would be a 3-dimensional slice at time t is equal to 0, t is equal to 1, t is equal to 1. So now your dynamics of the universe are about 3-dimensional surfaces evolving in time. And this is because of this 3 plus 1 split. Okay. So in here, this is governed by the Einstein field equations, which you don't have to know, I'm just writing it for completeness. And the main point is that on the left side of these equations, you have curvature terms. And on the right side, this TAB is a matter. So the idea is that you have matter in the universe, like physical matter, like radiation, dust, etc., that induces curvature in the space-time. In the 3 plus 1 picture, you have curvature that's evolving in time. So that's how you talk about dynamics. So, but these are 4-dimensional equations. How do these translate over to a dynamical form? So the idea is to get dynamics, there are many ways. This is not a unique way to go from this picture to this picture. It's a convenient way to do it. To get dynamics, what you use is something called the orthonormal frame formula. And I will not also go into this in too much detail because I don't want people to start throwing things at me. But the idea behind this is that if you assume that on large scales, the universe is what we call spatially homogeneous. And I'll explain what this means in a second. Then, the Einstein field equations can be written as a nonlinear system of first order ordinary differential equation at dynamic velocity. Does anybody know what I mean by spatially homogeneous? Yes?
That everything looks the same from everywhere.
Almost. So it's isotropic. What do I mean by homogeneous? So I mean, that's a good point. So when I say something is spatially homogeneous, I mean that it's translationally invariant. So if I have something like this, like a circle or sphere, and I take 2 points, and I move the 2 points, the sphere still stays the same. So I can translate, so this is invariant with respect to spatial translation. So on our largest scales, our universe is invariant with respect to spatial translation. It's homogeneous, and it's isotropic as well, but that's for another day. Okay? So the main point is the following. You can take these tensor equations that are actually 10 nonlinear, coupled, hyperbolic, partial differential equations that have no solution whatsoever, and you can reduce them to a dynamical system if you assume that the universe is spatially homogeneous on logic. Because you see, if I tell you that the only thing that's evolving is time, that's what it means to be spatially homogeneous. Nothing is changing in space, it's only changing in time. Yes?
2 questions. The first one, did Einstein actually do this equation himself?
Yes. Under 10 years.
10 years?
1905 to 1959.
So then he didn't know how to solve this, but he interpreted it?
So there's a funny joke behind this. Einstein, in the process of 10 years of deriving these equations, spent many years going to talks where he was giving people kind of previews of what he was trying to do. And in one of his latest talks, around the 1915 mark, David Hilbert was sitting in the audience. Hilbert figured it out, what Einstein was getting at. And Einstein knew that Hilbert knew what he was going to do. So he rushed on, and they had a race between the two of them, actually. Hilbert figured out what Einstein was trying to do in 10 years in 1 hour. That's how smart David Hilbert was. So he figured out these equations. They are his equations. But then he concluded in his paper, except for the most trivial cases, these equations cannot be solved. Lo and behold, 2 years later, Schwarzschild comes up with a solution of these equations. So they're extremely complicated to solve. But you can do this, and you can get a dynamic system.
Second question.
Yes?
So you said for the sphere one, you have 2 points you move them, they're the same?
The sphere doesn't change.
So what is that for reality for space? You're saying if I take any 2 points in space and I move them anywhere?
The universe is on the largest scale. So if you see a picture of the cosmic microwave background, for example, you can take any 2 points in the night sky, but the universe doesn't change its structure with respect to rotations or translations of those points. That's it. So our universe is a very geometrically special. Okay, so but what are these equations? So when you apply this formula, as I said, the field equations become a dynamical system. So you get three. The first equation has a special name for it because it was derived by an Indian physicist for a change. His name was Ray Chaudhuri. And his equation is called Ray Chaudhuri's equation. And I'm not saying this because I'm obviously biased. I'm just saying that it is actually the most important equation in cosmology. I will say that. Okay. There are many non-Indians that will agree with me on this. Okay, and it goes like this. So you get theta prime. I'll explain what these variables are. So prime means d by dt, as usual, okay, is equal to minus 1/3 theta squared minus 1/2 mu plus dt plus capital M. I'll explain these symbols in a second. I just want to write down the equation. So you get Ray Chaudhuri's equation. You get what is known as the Friedman equation. Or constraint. And that looks like the following. So 1/3 theta squared is equal to minus 1/2 capital R plus mu plus lambda. You get an energy conservation equation energy density / conservation equation, which goes like this. So mu dot, I shouldn't put dot, I'm using prime. So mu prime is equal to minus theta mu plus p, and then you get the longest of the equation, which is the curvature evolution equation. R prime is equal to what? 4/9 theta cubed plus 2/3 mu plus 3p minus 4/3 theta lambda minus 2 theta mu plus p. And that's it. So you get three dynamical equations, just like we have for other systems, and one constraint. Now, what are all these things? I have no idea, I just made them. I'm joking. But the point is, as you can see, using some formulas on which I'm asking you to take my word for, or you can look up the paper, it's very convenient. You can reduce these tensor PDEs to a bunch of ordinary differentials, just like we had for everything else we did. Now, what in the world are these symbols? I will tell you. Theta is what we call an expansion scalar. It tells you how the universe expands or contracts. If the universe can expand, it certainly can contract. That's what theta is. So Ray Chaudhuri's equation tells you the dynamics of the expansion rate or contraction rate of the universe. Mu is the energy density of matter in your universe. E is the pressure, so the matter of pressure. What else? R is the three-dimensional curvature of the spatial slices I drew them. And it evolves in time. So you have an R prime equation as well. And then lambda is known as the cosmological constant. It is one of the fundamental constants of nature, of our universe. Does anybody know what it is, the number?
Oh,
You don't have an idea? It's not 5. It's actually a very small number. It's 10 to the minus 122. About.
was it this
The cosmological constant represents what we call dark energy, or that's the belief anyway. And dark energy is responsible for the accelerated expansion.
Isn't this what you were arguing about the longest time?
Yes.
Where they were saying that
So Einstein,
and there isn't.
right, so this lambda here, this capital lambda, is responsible for the accelerated expansion of the universe, the dark energy. Einstein introduced it into his equations by accident and thought it was a mistake at first. But then it was later on discovered that actually you need this. So it was his biggest blunder, as he said, but the most useful one. Okay. So is that clear so far? So one covers the expansion of the universe. You have things that talk about the matter and pressure of the universe. R is the curvature, and lambda is the cosmological constant. Okay. So, but as we've been doing with everything else, we have a constraint. So I can use the constraint to eliminate one of the variables. It's the same thing. There's nothing, actually this is, in some sense, more easy to deal with than the biological systems because as of now, as you'll see, we only really have one free parameter. In the SRS model, we have like 7 of them, no bit. But it's much easier. So let me do that. And there's a hidden surprise when you use a dynamical systems method like this, and I'll tell you what it is. But I have to have it. So, can anybody quickly look? I erased the theta prime equation now. But just like in dynamical systems, I need one equation for every variable to have a closed system, right? I have not accounted for one variable. I'm missing one equation. Can anybody tell me what it is? Look carefully. Do I have an equation for theta? Do I have an equation for mu? Do I have an equation for r? Lambda is a constant, so whatever. What am I missing? Pressure. How do I take care of that? Any fluid mechanics people in here? Do you know? From atmosphere? No? No, I don't want to. Does anybody have an idea? How I can talk about pressure? I'm missing pressure. No. Okay. So, there's an assumption, which is actually a pretty good assumption. We can assume that the matter in the universe is what we call barotropic. That means that the pressure is proportional to the energy density. And this, how do I change a proportionality to an equation? I have to introduce what? Constant, right. So to fix this, I will assume that P, which is the pressure, is given by some constant W times mu. And that will allow me to close the equations. And in particular, what is this W? We call it an equation of state. And if you take courses in fluid mechanics, you will see this. Equation of state forever. And this W, which is a dimensionless number, describes the type of matter you could have in the universe. In particular, we assume that W strictly is between -1 and 1. And there are some examples of what values of W can be. So, in particular, so some examples. If W is equal to 0, that means your universe is filled with dust. Just straight old cosmic dust. If W is equal to -1, this means you have a second cosmological constant, which is quite possible. If W is equal to 1/3, it means your universe is filled with radiation. There are some more exotic states. If W is equal to -1/3, these are what you call cosmic strings. And the most extreme case, on the other end, is if W is equal to 1, this is what we call a Zeldovich fluid, or a stiff fluid. So this is valid at very early times in the universe. So now we have accounted for, and this is the only free parameter that will show up in our equation, this W. So now we have accounted for all the variables. Now I will use the constraint to eliminate normal equation. This is all fluid mechanics theory. As I said, I'm skipping about 3 textbooks worth of courses for this 30-minute lecture. But it's okay. We want to understand using what we know. So. Sorry? Okay. So I will now use the Friedman equation to eliminate mu, just by choice. I don't like mu, I will eliminate. And as a result, you get 2 equations. So the Jacobian equation becomes the following. 1/4 minus r minus 3rw minus 2 theta squared minus 2w theta squared plus 6 lambda plus 6w. And the r prime equation is so simple, it's laughable actually. And you don't expect it actually. Watch how simple it is. It's minus 2/3 r theta. Yeah. It's such a surprise when you derive it, and this just comes out as one term. Very nice. So just like our other examples, the entire evolution of the universe on the larger scales comes down to 2 ordinary differentials. I skipped a lot of stuff, obviously, but this is the answer that we're interested in. Any questions so far? Oh. So that's our dynamical system, and it has one free parameter, which is the W. So you can tell now stability will depend on what W is. And I should make this point that you can have mixes of these two. So you can have intermediary states like 4/3, which is like radiation plus dust or something like that. You can have mixes of it. Okay, so that's our dynamical system. So now what is the first step when we give, because I don't believe that these can be solved. I tried, it doesn't work. So what is the first step?
Isn't W -1
It is. Oh, you're right, I'm thinking of something. Try 3/4, I understand. So, you're right. Okay. Or 4/5. You can have mixes of it. Any number between -1. Okay, so what is the first step? Equilibrium. Equilibrium. As usual. Now you can see, actually, find the equilibrium points is actually the easiest. It turns out in the cosmology case compared to the biology case. That's because biologists tend to overdo everything. But also it's because the only way equation 2 can be 0 is if r is 0 or theta is 0. There's nothing to do here. If r is 0, set r to 0 in all of these, you get a solution for theta. Step 2, set theta to 0. Set theta to 0, you'll get a solution for r. So it's extremely simple to find the equilibrium. So let's see what else. And I claim there are 3 equilibrium points. Okay. So, and this is the surprise about this method. So when I told you before that the Einstein equations are impossible to find closed form solutions for, it turns out actually, unlike our previous examples, the equilibrium points actually mean something very significant to this dynamic. And in fact, the surprise is that the equilibrium points are solutions to the Einstein equation. They just aren't random points like in biology and game theory and stuff. They actually are solutions to the field. So in some sense, there are new ways to find solutions to Einstein equations using this orthonormal frame formalism. So what are they? So one equilibrium point. So I'll call this equilibrium point 1, or just P1 maybe for short. So as I said, the simplest thing to do is to just set in turn theta to 0 and y to 0 and see what happens. So if you set theta to 0, so remember I'll call it theta star or star. So set theta to 0, and then you solve the R equation. What do you get? You get 6 lambda plus w lambda over 1 plus 3. Now, let me ask you, what is significant about this solution? What does it mean to have theta equal to 0?
R is constant.
Say?
R is constant.
No, theta is equal to 0.
Yes, universe is neither expanding nor contracting.
Exactly. That's the key point. And so if it's, something is not expanding or contracting, what is it by definition?
Static.
Static, that's right. Very good.
Not even
So theta is equal to 0. Remember, theta is the rate of expansion in scalar. So if it's not expanding, it's static. So the first set of equilibrium points represent static universes. And now, it depends on the sign of R, how you subclass these static universes. So let me ask you a geometry question. If I have something that is spatially homogeneous, and actually I also made another assumption which Spiros alluded to, but I actually didn't admit it at the time. Not only am I assuming spatial invariance, but I'm also assuming rotational invariance. So, if I have some shape, easy geometry question. If I have some shape and it's invariant with respect to spatial transitions and spatial rotations, what are the only 3 possible geometries I can have? Sphere is one of them, in 3 dimensions. So, what are the only possible 3-dimensional geometries I can have? Sphere is one, planar is another. Perfect. Why did you say hyperbolic? Okay. Right. There's only 3 possibilities. You can have a sphere or spherical geometry. You can have a hyperbolic geometry, which is like a saddle. Do not get confused, I don't mean the same hyperbolic at equilibrium. Or you can have a planar geometry. Only 3 possibilities. In the first case now, is the curvature positive, negative, or 0 for a sphere? Positive. So R would be greater than 0. For a hyperbola or a saddle, is my curvature negative, positive, or 0? Negative. And for a plane, is it flat? Yes. So not only do the first set of equilibrium points represent static universes, but we have a subclass now depending on the sign of this. So, for point 1, if R star is greater than 0, these are static spherical universes. If R star is less than 0, these are static hyperbolic universes or negatively curved universes. And if R star is equal to 0, you have static flat universes, or just plain old Minkowski space-time of special relativity. Static and flat. Now, what is the only free parameter in R star? W. And W goes between -1 and 1. So depending on the sign of that, or the sign of W, we will have these types of cases. So let's see what we have. And in fact, the case where R star is greater than 0 and it's static, this has a special name. It's called the Einstein Strategy. It's actually one of the first solutions he found. Yes? Static and flat, if you can imagine. I meant to say flat. No. Sorry, I lost my interest in writing. Okay. So let's see. Let's analyze this equilibrium point and see what we have. But in general, the first equilibrium point represents classes of static universes, because no matter what theta is equal to 0. So, if R star, I'll just write out R star, is equal to 6 lambda plus W lambda over 1 plus 3, 0. What is the only way R star can be less than 0? As you can do the analysis, it means that 6 lambda plus W lambda over 1 plus 3W must be less than 0. Now, as I said, lambda is just a constant. It's positive 10 to the minus 1, but it's a positive number. And W goes between -1 and 1. So the only way this can be negative, as you can show, is if W is strictly between -1/3 and 1. So, for any matter where W is -1/3 strictly less than and up to 1, you'll have R star less than 0. Greater than 0, sorry, I'm doing the close case. So it will always be an Einstein static universe equilibrium point if W is between -1/3.
Is that because the top doesn't matter at all because it's just one number? So you're facing around the denominator? Yeah.
Essentially, yes. But you can just do the algebra of the inequality as well. Oh, question. Yes, yes. So I was doing the closed case, but I wrote the wrong sign. Okay. Now the second case, R star less than 0. So when do we have static hyperbolic universes? Is when 6 lambda plus W lambda, 1 plus 3W is less than 0. And this is kind of more or less the opposite. Right? So in this way, this will only happen when W is strictly between -1 and -1. You'll get that. And the final case, you'll have a Minkowski or flat universe with what? See? Did you see the answer? Oh, okay. And R star is equal to 0 if this is equal to 0, and that will only happen in the extreme case when W is -1. What? You did it. That's it. This is a -1, not a minus blank and box.
What happens if W is equal to -1/3?
You have singularity. I do not want to. Actually, it's a very important case. What you brought up, you see the curvature blows up, goes to infinity. So that's an example of a cosmological singularity. We've talked about that. Okay, but is everybody clear on this? So it's the same thing. It's actually easier than the biology example. I have my dynamical system. I found the equilibrium point. And now I just look at the sign to see what I have. And the sign depends on the front. Okay, that's the first set of equilibrium points. In 1 minute, I think I can tell you the second set. Because really there's one equilibrium. So these set of equilibrium points happen when I set theta to 0. Let me do the other one now, set R to 0. The equilibrium point. No, I have to do it now on Wednesday. I was going to do it, I thought I'd have time, but I did not. Probably because you asked so many questions. No, I thought I'd have time. Okay, so now we will set R to 0. And what does it mean if I'm starting only with solutions of R to 0? What type of points are these? So, I've not set theta to 0, just set R to 0. So they're flat. So these are flat. To be proper, I should say spatially flat. Because I criticize other people when they do not put spatially, so I should do it. And what happens is you get the following equilibrium. Theta star, R star. If you set R to 0 in that equation and you solve for theta, you get the following. Very easy. Square root of 3, square root of 1, and theta. And actually, we can write down the second one as well, because it's just the minus of this. So there's 3 equilibrium points in total. The Einstein static universes and these flat universes. And these are also solutions to the field equations as well. In fact, these are what we call de-Sitter. And now you see theta is not 0, it has a number. If it's plus, so theta is equal to plus square root of 3 square root of lambda. These are expanding. I'll just put ds for de-Sitter. And obviously if theta is equal to minus root 3 root lambda, these are contracting. And I literally mean this. So if you have 2 observers in these universes that are moving in this universe, when I say they're expanding, I literally mean they're expanding apart. So one goes like that, and one goes like that. And the rate of this divergence is what you call theta. But you can go the other way too. So you can start, if the universe is contracting, as these observers are moving along these lines, they will eventually reach the same. 1 second, I'll get you. Okay. So these are the 3 equilibrium points. Now, which I must say for Wednesday, what is now the next step? Jacobian. So we will now analyze now, based on the eigenvalues, which of these points are stable, unstable. Any questions? It's the same thing. But this is much, much more interesting than anything biology does. I know. I've given up trying to edit and find out the rest. So we had the theta dot equation, or theta prime equation, which was 1/4 minus r minus 3 rw minus 2 theta squared minus 2w theta squared, plus 6 lambda, plus 6 w lambda. And we had the r dot prime equation, which is minus 2/3 r theta, after a bunch of. Then I found 3 equilibrium points. So the first equilibrium point corresponded to the case where theta star was 0, and we saw that that meant these are static universes that do not expand over time. So these are the static solutions. And they were in general given by theta star r star is equal to 0, 6 lambda plus w lambda 1 plus. And then I broke down cases for you where r would be less than, greater than, equal to 0. And the important case was when r is greater than 0, and these were the so-called Einstein static universes. And so forth for the other cases. And then I found 2 more equilibrium points which were just conjugates of each other, the so-called Heterogenic universes. And these were so equilibrium points 2 and 3. And one was theta star r star. So these correspond to cases where r star is equal to 0, and these are spatially flat universes. Because the curvature, which is r, is 0. So these are flat. And in particular, we had plus square root of 3, square root of lambda 0. And then we had theta star r star, which is minus square root of 3, square root of lambda. So that's where I left you off. And this solution, because it's plus, theta is plus, is an expanding universe, which is the expanding de-Sitter. And this is minus, so theta is minus, it's contracting, you have a contracting de-Sitter. This is what they were working out in that picture, but in a much more difficult way, actually. I can show you after. Dynamical system is very beautiful because it allows you to do things that otherwise would be very difficult to do. Because we can get, I've not actually solved the equation. You see, with the nonlinear systems, all the nonlinear systems that we've done, I don't even care about solving them because I can get so much information from equilibrium points and eigenvalues and things like this. I can sketch the entire solution without actually having to solve the equation. So that's why I left you off last time, and today we will do the stability analysis. So, eigenvalues slash stability. So, the first thing to do is to set up your Jacobian matrix, and the quickest way to do this is to call one F1 and to call the other one F2, as I've been doing. Eventually you won't need to do that, but just to keep track, it's easier to do like this. So then your Jacobian matrix is simply given by partial F1, partial theta, partial F1, partial R, partial F2, partial theta, partial F2, partial R. And now you just compute, as usual, partial derivatives. So, in general, you get the following. Minus theta, 1 plus w, you get 1/4, minus 1, minus 3w, you get minus 2r over 3, and minus 2 over 4. Very good. Everybody clear so far? So it's the same thing as usual, just computing partial derivatives. So now, I want to, that's my Jacobian in general. I would like to determine eigenvalues related to each point, as usual. Okay. So let's do it. So what happens? We must substitute our equilibrium point, as usual, into our Jacobian matrix, and then we will compute the eigenvalues. So, I guess I should call this point 1, and then this should be point 2, and this should be point 3, just to be. So, at point 1, where theta is equal to 0, and R is this wonderful looking number, we have the following, that the Jacobian, if you just substitute into that, it becomes the following. You get 0, you get 1/4, minus 1 minus 3w, minus 4, 1 plus w lambda, 1 plus 3w, and 3. Straight substitution. Question? Oh. Okay. So you get 2 zeros. And now you just compute the eigenvalues, which is a trivial thing to do. What's trivial if you have nothing? Lambda 1 you find is minus. So I've given you 3 types of these questions on your review sheet. All 2x2 systems. And it will give you practice on computing eigenvalues. So minus square root of 1 plus w square root of lambda, and the other eigenvalue you get is square root of 1 plus w. Now, so is this a source, sink, or saddle? Why is it saddle? Very good. So this is always going to be negative, because these quantities are positive, and this is always going to be positive. And moreover, why are they always going to be positive? Is because I'm assuming w can be between minus 1. If you remember our assumption. Now, there are some interesting, maybe there's not enough physicists in this room, so you will not respect this idea, but there are some physicists that have taken this idea that what if you have a negative cosmological constant and you get complex eigenvalues here? You get all sorts of weird dynamics actually. So there are some interesting ideas behind this, but we can talk about it later. But for our purposes, as I said last time, we are assuming that lambda is roughly this very, very small positive number. And w is between minus 1 and 1. So you're right. So therefore, because lambda 1 is less than 0, which is lambda 2, this is a saddle. So therefore, what we can say for this model, which are my spatially homogeneous and isotropic solutions, if you remember, that was the assumption we made, the sphere, the hyperbola, and the plane. Yes? We do consider the weak to be zero. It can be zero.
No, sorry, sorry, the root becomes 0, the mean becomes 0, and so I know.
That is a complication that we do not want for this case. Because there's some deep physics involved in why that is. So I'm saving you from this actually. So, therefore, for this model, all of the static solutions are saddle models. I will ask you this because I will ask you on the exam as well. As I asked you on the review sheet, what is the dimension of the stable manifold? Of the stable manifold? Very good. So, a quick way to write this, if you remember, we denoted our manifolds by W as W, U, Ws. If you go back to your notes, so a quick way to write this is dim Ws, dimension of stable manifold. What is the dimension of the unstable manifold? 1. Great. W, U. And what is the dimension of the center manifold? 0. There's no center. And that's William's question. I do not want to deal with center manifolds. I'll show you why in 5 minutes. It's very complicated. Okay. And of course, dim of WC. And what does this mean? It's a nice thing to impress your friends with, but what does it mean? That the dimension, you have essentially 2 manifolds here. It means the following. It means you have, because you have a one-dimensional stable manifold, or you have a stable manifold to begin with, that means there are some orbits / solutions that are attracted to this. And if you have also correspondingly an unstable manifold, there are also some solutions that are repelled by this. So that is the significance. In the neighborhood of the point, because remember, we define manifolds in the neighborhood of our equilibrium. So that's what it means to have a stable and an unstable. Any questions? So that's for one of the equilibrium points. What about my de Sitter universe? What? And I just realized I erased my Jacobian. Oh no. Okay. That's okay. I can just ask you to recall it. So at point 2, which was theta star, r star is equal to square root of 3 square root of lambda 0. The Jacobian, as you can confirm, takes the following form, or form. Namely, you get minus root square root of 3, 1 plus w, square root of lambda. This stays the same. You get 0 here. You get minus 2 square root of lambda over square root. And what are the eigenvalues? You get 2 as you expect. You get lambda 1 is minus 2 square root of lambda square root of 3. And you get that lambda 2 is equal to minus square root of 3, 1 plus square root. Okay. Is this a sink, source, saddle, or something else? Why is it a sink? Just 2 names. So, clearly, lambda 1 is always less than 6. Start there. And lambda 2 will also be always less than 0 if minus 1 is less than w, which is less than equal to 1. Even if w is equal to minus 1, which is the special case here, and then therefore lambda 2 is equal to 0. Remember I said, as long as only one of the eigenvalues is 0, you can always look at the signs of the other ones to determine the sigma. So even if w is equal to minus 1, this will still always be negative. So it's still a sigma. Remember I said. But lambda 1 is still less than 0, so this is still. So what does that mean? So, what is the dimension of the unstable manifold? 0. What is the dimension of the stable manifold? 2. And what is the dimension of the center manifold? So it's purely attracting. Dim WS 2. Dim WU is equal to dim WC, which is equal. So therefore, this point attracts. Further now, we can answer one more question. What type of stable is this point? Asymptotically stable. And why is it asymptotically stable? Both are negative. So by the Untitled theorem, we can say one more thing. Further, by Orthonormal stability theorem, this point is asymptotically stable. As long as W does not equal -1, because both eigenvalues have to be negative. Since lambda 1 is less than 0, lambda 2 is less than 0. As long as W does not equal 0. So there's two ways to determine asymptotic stability. Lyapunov stability theorem. And all you're required to show is that both or all of your eigenvalues are strictly less than 0. Any questions? So it's interesting. We have a bunch of static universe possibilities that are saddled. And we have this expanding state that is asymptotically stable. It's a synchronous. Interesting. I wonder what will happen if you look at the final equation, at the contracting deceleration rates. Let's see. As you can imagine, I don't really need to do the computations over. Why is this? I just have to put in minus signs. So just switch the signs. Because you see the calculation is invariant with respect to a minus sign. Because the other point is just minus with 3 or plus. So if I put a minus here, it will cost me a plus sign here. And then therefore I'll get 2 plus eigenvalues. So this should be 0.3. I just won't be great. Out of sheer laziness. So, is this a sink source or something? It's a source.
Is that usually the case with conjugates?
Not always, but in this case it turns out to be correct. This is a hence it is unstable. And now I will ask you again, what is the dimension of the stable manifold? What is the dimension of the center manifold? And what is the dimension of the unstable manifold? 2. So therefore, because this equilibrium point only has associated to it an unstable manifold, it is repelled. It repels all of it. Therefore, repelled. Very good. So this is the first system which we've done, which has a sink, a source, and a setting. But for all values of W, no matter what you choose W to be, you'll always have that the saddle universes will be a saddle, and you'll always have the contracting universe as a source, and you always have the expanding universe as a sink. So what do what we actually have in other discoveries, a very cool thing has emerged from this analysis. We have something that connects a sink, a source, and a saddle. What is that called? Does anybody remember? If I have in sequence a source, a saddle, and a sink. Heterogenic orbit or heterogenic sequence? Sequence. Very good. Very interesting. I think so. I should erase. I forgot what order I'm at. So I should erase the second one.
You just did this one.
So I should erase the first one. This happens to me a lot, actually. A lot of students got angry at me in my first year class. They wrote all this stuff down, and then I have a habit of, I guess, absent-mindedly talking to students during the class, and then I went back and I erased what I just wrote. And they were not happy about this. Yeah. That's the second. Okay. So, irrespective of what W is, the point 1 is always a saddle. Point 2 is always a sink. And point 3 is always a source. In other words, what this implies is that you have a heteroclinic sequence that connects. Remember, so what is the definition of a heteroclinic sequence? I kind of just told you.
Start with the source and some shadow inside.
Right. So the source goes to a saddle, or maybe you have more than one saddle. As long as you start with the source, you have a bunch of saddles in between them. And that's interesting. So I'll explain the significance of this in a second, but now I kind of see. So let's do something. So as I said, I wrote this up kind of quickly in the car. Well, I was not right. I was in this. And so to do these numerical solutions, you have to pick a value for W. So I just picked, just to start with, let's just do 1/3, which corresponds to a universe with radiation, if you remember. So let me take that. And then I got to also draw these equilibrium points as well. Maple is not visible. And then I will. So that's what the base portrait looks like. And just to keep it in context, so the different equilibrium points are there. Maybe blue was not visible, but you can kind of see. So what are the individual points here? So red, just to keep a legend. I forgot the code to add a legend to the figure, so I'm writing it by now. The red point is this one. I think I wrote blue is the second point here, which is the sink. And green, obviously, is
So are these equilibrium points in the universe, or they're different universe?
that's what I'm going to talk about. So, as you can see, you can clearly see that the red is a saddle point. You have some that are attracting it, some that are repelling it. You can see blue is very clearly a sink of the system. The Mathematica is very weird with some of its orientations at first, so pretend it's not like that. But as long as you notice the sink and source behavior, green is clearly a source of the system, blue is clearly a sink. So you have these, and look, they're on polar opposites of the phase portrait as well. Just like we expected from the conjugate behavior as well. So you definitely have in this system, you have expanding universes that are a future state of the system, starting from some generic contracting state. And you see there's orbits that connect all 3 points. If it was drawn more better, but you can clearly see a heterogenic sequence beginning of this. So we can talk about that in 2 minutes, because I don't want to give you the impression that they're different universes, actually. They're states of one universe. So let's talk about that. And I'm not actually, I should make this point. What is the next step I always do after I finish analyzing the eigenvalues? Even on your review sheet, what is the next thing I ask? The fourth thing. Starts with the bifurcation. I cannot do that for this moment. And that's Liam's why I didn't want to do lambda is equal to 0. If you set lambda is equal to 0, you get only center manifolds. You get no stable or unstable manifolds. All your eigenvalues are 0. So this is actually leads to what we know as exotic bifurcations. And they cannot be determined by looking at the Jacobian matrix. That's why it's called exotic. So usually what we've done is we've linearized the system, and then we've seen where the Jacobian is equal to 0. In some very highly nonlinear dynamical systems, you cannot do that, because the Jacobian is useless. When you set certain parameters to 0, you just get a bunch of zeros. So cannot be determined by Jacobian. But they still are there, and this system in particular has a very specific type of bifurcation, and it's called something actually. 1607. These are called the following. The type of bifurcation you get is what is known as the Orthonormal degenerate bifurcation. And I will spare you the details. I will simply ask you to. It's too complicated to cover in this class because it relies something on what we call center manifold. But if you want to look it up out of shameless self-promotion, once again, you can look it up in archive, and it's 1607.02. Very interesting behavior happens actually in the bifurcation, but it cannot be determined by linearization. So, what does this mean? I keep calling these equilibrium points universes, but I don't actually mean they are different universes. We still only have one universe. In any dynamical system, though, what do the equilibrium points represent? They represent different states of the system. So this represents different states of one universe as well. It's not that there are different states, they're different models. So we have 3 equilibrium points, which means that this universe, at least under the assumption of the geometry that we are dealing with, the homogeneity, has 3 distinct states in its evolution. In particular, so it started off in this contracting space, contracting to what? Big Bang. At t is equal to 0, let's say. Then for some interesting thing that we don't understand why, it hit this saddle behavior, which was our static universe. And then somehow we ended up where we are today, which is the expanding state. So our universe is expanding precisely like that. So our universe has 3 different epochs. Our contracting epoch that goes to the Big Bang. There's some saddle behavior intermediary and then our final expanding state. And that's where we are now. I don't. That's the other key thing. So, how we got the Einstein field equations, how I wrote down the dynamical system, if you remember, I made a bunch of assumptions. The two assumptions I made was that, in general, the model I'm dealing with is spatially homogeneous. And isotropic. But this behavior depends upon the geometry I assume to start with. It's very specific. I assume that the space-time is homogeneous and isotropic. If I drop one of those assumptions, I get a broader range of equations that have more equilibrium points, at least 10, 8, 9. Each one of them has different stability equilibrium. In some of these assumptions, if you drop isotropy, for example, you don't get that the saddle is intermediary. Maybe you get that a static universe is the final state, which is Robert's question. So these equilibrium points crucially depend on the assumptions you make. And that's very tricky because nobody knows precisely what the configuration was of the very early universe. So I've assumed in some sense that the early universe in my model, or Friedman's models, are very clean to begin with. But it's not always clean. Not necessarily. But I have data to prove what I do. He's trying to start a fight. No. Well, I mean, there's some justification before this thing. And what is our justification? It's this thing. If you look at a radiation map of the night sky, which is a cosmic microwave background, if you also wipe out the night sky. You see, it's kind of a poor picture. I'm trying to find a better one. So this is not on the largest scale. If you look roughly at this picture, at very large scales, there is homogeneity and isotropy up to a very high percentage. So there is some justification, or very strong justification actually. And plus, we know that the universe is expanding. That's a confirmed. So there is justification. But as I said, if you drop one of these assumptions, the equations become much more complicated. And in some sense, it must be the case because the early universe you expect to be chaotic and all these types of things. So it's not necessarily a good assumption to assume it's very clean to start. But that we can talk about. But any questions on anything about this? Not whatsoever. So if I gave you Einstein's equations, you could solve them. No problem. So expect it on the last question. Until. No, maybe not. Why not? You can do it. You've done this. Why can't you? Really? No, I want you to do that. But it's good practice. It's very good practice. And you say I'm crazy. I can say it. But now I'm being accused of it.
I'm merely being bird.
Anyway, so I just wanted to say, you've been a very good class. I thank you for putting up with me and all my laziness and jokes. But if you ever need anything in the future, please do not hesitate to email me or contact me or whatever. It was very good to see you. Thank you.
What fire? Oh. It's doing this. Is it cold outside? Yeah, bro. Sorry, you probably need to get through. Are you going to take that down or not?